All right, so we're going to start. Welcome to this C2 Smarter seminar series. Today I'm delighted to welcome here at NYU Dr. Eleftheria Kantu. She is an assistant professor in the Civil and Engineering Department at the University of Illinois, Urbana-Champaign, and her research focuses on sustainable and electrified transportation systems, planning and management. She has worked as well at the National Renewable Energy Laboratory, as well as the City and Regional Planning Department of the University of North Carolina at Chapel Hill. And she actually is quite distinguished, right? Because she received the NSF Career Award in 2023. She is also a 2023 Council of University Transportation Centers new faculty award recipient, and as well as an Illinois, Indiana Sea Grant faculty scholar. Particularly for me, so she's also my academic older sibling, since we have the same advisor, PhD advisor. And so I'm very delighted to welcome her here. So please welcome Dr. Kantu.
Thank you very much, Professor Mignon, for this wonderful introduction. And thank you for the opportunity to be here. Thank you for coming. We have a presentation on alternative fuel vehicles, evacuation planning, and refueling or charging infrastructure to support faster evacuations. This is joint work with my students in my group. I'm going to introduce my team a bit later. But today's seminar is going to go as follows. We're going to go through an introduction, pretty much giving you a bit of an idea of the topics that my research group works on, and then focus on the two main topics of today's presentation: evacuation and route planning for alternative fuel vehicles, since we have a heterogeneity of vehicle fuel types on our transportation networks. We have gasoline and diesel vehicles that are pretty ubiquitous, but now we have the advent of battery electric vehicles, as well as promising future for other technologies such as fuel cell electric vehicles, etc. I'm going to introduce the objectives, the methods that we developed for tackling this problem, as well as numerical experiments in both benchmark and real-world networks. Taking advantage of our prior work on evacuation route design, we also propose a refueling and recharging infrastructure location planning model in order to supplement infrastructure that can facilitate faster evacuations in a setting of alternative fuel vehicles. Again, scope, method, numerical experiments will be presented, and then I'm going to close with an ongoing and future research agenda in this space, or tangential spaces with a few ideas on future research in this field. Okay, when it comes to work that my group is currently working on, we're developing quantitative models, algorithms, and data analytics solutions to emerging mobility problems, particularly focusing on enabling sustainable transportation systems. So we are tackling the grand challenge of transportation decarbonization. A thrust of our research is tied to planning and management of electric vehicles and their infrastructure. Work in this space that we have completed includes the evacuation route planning model that I'm going to delve into today, as well as planning over a horizon for distribution and allocation of investments tied to incentives for electric vehicle adoption, so that we can formulate problems that public agencies need to solve to determine how they can meet emission reduction goals during this transition phase. In the thrust of data analytics for sustainable transportation systems, we have conducted work towards defining transportation energy vulnerability. So this is a concept that stems from the theory of social vulnerability and accounts for exposure to transportation energy burdens where different populations are more or less sensitive to, depending on their demographics, and the notion of adaptive capacity, because in certain locations we have alternative modes that shares of populations can have access to and not depend on the automobiles and fueling for those. Last but not least, we conducted a very well-cited study looking into the research question of equitable allocation of electric vehicle incentives. We examined the California Vehicle Rebate Project And we demonstrated that the early rebates for electric vehicles were primarily allocated to wealthier consumers, while policy mechanisms such as income caps in the process resulted in more equitable allocation of the incentives in the aftermath and as time went by. The driver for our work is, as I mentioned previously, the decarbonization challenge. We know that the transportation sector is the most, the sector that relies primarily on fossil fuels, and overall, in a global setting, 31% of the carbon dioxide emissions are attributed to transportation use. So when we're thinking about decarbonization opportunities, in the portfolio of the transition, massive shifts towards electrification seem to be subset of the solution space, right? So without changing our lifestyles, particularly in the United States, transition to zero tailpipe emission vehicles are an effective solution towards decarbonizing portion of the transportation when they are effectively matched and coupled with clean electricity generation, so the integration of more renewables, while also coupled with other solutions such as public transit electrification, active transportation, systems development and investments for safer infrastructure in the space, as well as attitudinal and behavioral changes that can be both induced by technological advancement, but also with market-based design mechanisms. At the very same time, as scholars and the next generation of engineers, we need to rethink the objectives that we set as a goal for our infrastructure in the transportation system, planning. And I say this because we see that often our investments tend to disproportionately negatively affect disadvantaged communities and communities of different socioeconomic statuses. So particularly as we expect greater impacts of climate change-induced hazards, we need to be cognizant on how funding is being allocated to serve meet goals of diverse communities. Last but not least, in a United States where we're expecting climate impacts such as hurricanes, extreme floodings, and wildfires to become more and more frequent and of increased intensity, scholars and the workforce of the future will be asked to fortify infrastructure that powers the next generation of transportation systems. Okay, this was a bit of an introduction on the work that actually, the work and the issues that actually motivate us. Focusing on evacuation route planning for alternative fuel vehicles, you can scan the QR code to find the openly accessible paper that we wrote. This was published in Transportation Research Parts. It's joint work with my PhD student, Ms. Denisa Purba, as well as our collaborator, Dr. Voyages. In 2023, I was approached by a journalist from NPR for Northern Colorado who asked me, what is the decision-making process that agencies take into account when deciding where fast charging is going to be placed? Because it seems that a lot of fast chargers are located across or along rural corridors that electric vehicle demand has not materialized yet. There's low electric vehicle adoption in these areas and low utilization, projected utilization of the local community. And it's important to consider the differences between different locations for charging, such as home, destination, and en route charging along major corridors. Home charging is prevalent at the moment. Early adopters of electric vehicles find the most convenient to charge at home. And that's why the electric vehicle paradigm is very different than the gasoline vehicle paradigm. You cannot refuel your vehicle with gasoline at home. Of course, there's opportunities to identify as part of your trip chain, stops within your day where you can, when you can recharge while you're pursuing other activities, and you are very productive in terms of utilizing your time for charging to pursue shopping or recreational opportunities. But at the end of the day, en route charging facilitates these long distance trips that are creating range anxiety for a lot of prospective electric vehicle users. So that's why we see a lot of these chargers along rural corridors, and there's the objective of the US Department of Transportation towards densifying this network. The location is being done considering habitual patterns, regular travel patterns, but these infrastructure might also help during non-habitual patterns that are observed when we are having an evacuation order in place. And I was able to discuss more about these issues that you're going to see as an outcome of this presentation with journalist communities in Houston and in Florida, which our research translates very well for these hazard-prone locations. Mm-hmm. Okay.
If we can.
Okay. Sorry. Thank you. Okay, so for this particular study, it is important to highlight that extreme events are happening more and more frequently. These prompt emergency responses in these regions. In the state of Florida, in 2022, during Hurricane Ian, there were 14 parses that mandated evacuation via orders. And you can see on your right-hand side the evacuation routes designated in Harris County in Texas. That includes Houston. You see all the blue links on the transportation network being signified as major evacuation arteries, as well as the yellow signified corridor that actually denotes the portion of the transportation network that can change direction so that it can accommodate, increase capacity to accommodate greater share of the flow, since during evacuations we tend to have movements away from hazards and not towards hazard. Towards hazard, we usually see coordinators and emergency responders moving to, but predominantly the population moves away from the hazard. Looking in the literature and practice, we observe that we have outdated evacuation plans that are not keeping up with alternative fuel vehicle specifications. Why do I say that? Federal Highway Administration and the Department of Homeland Security suggest designing evacuation routes so that they can go through respite sites that might include gas stations. However, there's no specific recommendation for alternative fuel vehicles. In the state of the art, evacuation design often includes the assumption that there is no range limitations for the vehicles that are traversing the network, or that refueling infrastructure and recharging infrastructure, if needed, is ubiquitously accessible. We know that's not the case. These assumptions are acceptable for gasoline vehicles, but not necessarily for battery electric or the new emerging vehicle technologies. And interestingly, we've done an analysis in the location of South Florida, where we center our focus, where we find out that gasoline stations are available almost 2 to 3 miles on the network. So pretty ubiquitous, not a problem there. That's not the case with alternative fuel vehicles. When we are looking into battery electric vehicles specifically, we need to highlight the following shortcomings. The battery driving range of battery electric vehicles is 60% on average of that of a gasoline vehicle. The network is sparser, and it's okay that it's sparser, but what matters is also charging session much more time consuming than a gasoline refueling session. Last but not least, evacuation displacements tend to span distances that are often larger than the driving ranges of contemporary electric vehicle models. You can see an instance from Hurricane Irma's landfall, a study that was conducted by Medak Kakaburi, and demonstrated that users of the transportation network tend to find shelter from Miami, locations like Jacksonville, or even crossing state lines. So in these instances, charging infrastructure is necessary to facilitate evacuation. Okay, I want to highlight first the pictures here, just as a reference point on what we're trying to achieve in our analysis. You can see on the picture in the upper area that we have an evacuation route designation in DC. And for you that travel at the Transportation Research Board annual meeting every year, you might be able to highlight all these evacuation routes with appropriate signage. On the map, we can also see in St. Johns County in Florida, directed links on the network, maps that are provided for information of the users of the network, along with the designated evacuation zones so that travelers and motorists are familiar with where they need to go in advance. So what we aim to do in our study is to designate routes pretty similar to what the map of evacuation routes in St. John County, Florida provides to their constituents, but do so for alternative fuel vehicles where we account for the need for share of the motorists to reroute to access infrastructure, make sure that it's feasible for them to access the shelters on the way to safety, and maintain certain characteristics that are important for efficient evacuations. So we are modeling the diversity of vehicle fuel types. Concurrently, users of gasoline, battery electric, and other potential fuels on the network can be accounted for through our modeling exercise. And we have the following routing characteristics: seamlessness, where we provide one path to the shelter for every evacuee origin. This reduces confusion, enables better coordination from the agencies, and enforcement efforts. And this was an artifact that was realized in the aftermath of Katrina, where a lot of drivers reported confusion as they reached intersections and they didn't know which way to go, a fact that resulted in delays and congestion. Seamlessness property is enforced by spanning tree constraints. Now, the contraflow property suggests that we can reverse certain road links direction to increase capacity and enable better utilization of the network given the evacuation flow definition. So this is enforced by contraflow side constraints. Okay, the preemptive evacuation route designation is going to be fast, seamless, account for contraflow traffic control, account for refueling or charging time for these alternative fuel vehicles, guarantee access to chargers or refueling stations, and address the diversity, different shares of different vehicle fuel types on the network. We're going to determine evacuation routes concurrently for K vehicle fuel types under an assumption of existing independent networks for those vehicles. And that's important because network providers are industry entities who deploy infrastructure without really any examination of evacuation issues, right? They do that in order to maximize utilization, serve demand, maximize electrified miles, or maximize profit, whatever their objective is. It's meeting habitual travel patterns, not really evacuation infrequent needs. So we have a K minimum spanning tree problem for K alternative fuel vehicle types and hop constraints that enable us to capture the refueling or charging needs for vehicles with limited driving range. And here's the conceptualization of the notion of the hop constraints, because that's an important consideration. We are going to assume tau sub k being a natural number of transportation links whose summation of distance is a proxy for the driving range of the vehicle fuel type K. Now, if demand originates from tau or more hops away from the shelter, which is the case here for node I, when tau is assumed to be 2 hops, then evacuees need to be routed through the refueling infrastructure node M before they reach the shelter. Just because the driving range is not enough, so they need to access refueling infrastructure. However, if evacuation originates from node J, that is accessible to where the center is accessible within one hop, because upstream demand, because of the property of seamlessness, needs to pass through the refueling infrastructure, they will be rerouted also like this, maintain one route and tree structure to the center, and enabling easier communication via map of the evacuation route to the constituents of the region. The property here is that we capture refueling and recharging time, and this is proportional to the distance between the evacuees origin and the shelter, making sure that the evacuees recharge or refuel as much as they need to so that they can access their destination, their safe destination, without really spending time or delaying their access to safety. The methodology is as follows. Data inputs include the origin, destination, evacuation, demand matrix, the shares of alternative fuel vehicles on the network and their specifications, average driving ranges, existing refueling station location specifications, meaning refueling rates and recharging rates, as well as the location nodes on the network, the transportation topology and locations of shelters or exit points. Objective, minimizing the total travel and recharging or refueling time on the network, subject to constraints that maintain seamlessness, contraflow, account for the need to reroute to access infrastructure for refueling or recharging purposes, and flow conservation, non-negativity and integrality constraints are baked in. The solution approach is a math heuristic approach. A path-based decomposition is included, and then have a Branson price algorithm with column generation. Our output will be the designated evacuation route for its vehicle fuel type, travel time measured, and the sensitivity regarding the network charging infrastructure or refueling infrastructure locations, driving range, and the composition of different vehicle fuel type shares. Okay, so I just want to focus on the conceptualizing the problem. On our objective function, we are minimizing in the first add-on the total system travel time. We are capturing congestion, so we're using a Bureau of Public Roads function. Average link performance depends on the vehicle flow, plus the total system recharging or refueling time is accounted for. In our constraints, we have flow conservation, really important in the network setup, but we also have tree and subtour elimination constraints. These guarantees the property of seamlessness, so one route to safety for its vehicle fuel type. Then we have the contraflow principle, and this needs to hold at the network level for all vehicle fuel types, so meaning that its direction, its link can be only utilized in one direction, and this should hold for all vehicle fuel types on the network. We have evacuation tree constraints that pretty much track the location of the evacuees on the network with respect to the shelter, and refueling hop constraints that where we track the need to reroute to access refueling infrastructure on the way to safety, maintaining the structure of the evacuation tree. Okay, this is a link-based formulation, mixed integer nonlinear program. The size of the problem increases as the network size increases, so we are pursuing a path-based decomposition in this process. We still have inefficiencies in terms of the nonlinearity of the link performance function, the integrality of the new variables that we're using at the path level. This is lambda. We realized that if we relax the integrality of the new variable lambda at the path level and we fixed the link performance, then the path-based formulation allows for dancing with structure, which is solvable with column generation. And we pursue the following algorithm. We start from a path-based reformulation because we have the link performance function that is dependent on the flow. Then this would dynamically change as the flow changes. So in a restricted main problem, we seek an evacuation path that essentially minimizes travel time Out of the set of feasible solutions that adhere to path-based traffic assignment constraints, tree constraints, and contraflow constraints. From this process, if we are able to fix the flow and deliver the link performance, so we are solving a pricing sub-problem in this process, trying to find an improving evacuation path for its evacuee zones in its vehicle type that adheres to shortest path constraints, hope constraints, and refueling decision constraints. If we are able to determine a path with a negative reduced cost, then we are able to expand the feasible set of our restricted main problem and solve for it again. Otherwise, we check whether integrality holds. Yes, we're done. No, we branch and we continue the iterative process. We apply the modeling framework to the benchmark network of Sioux Falls, South Dakota. It's not because evacuations often happen in this network, but it's because we have a lot of data, and it's a network that has been studied by several of our colleagues. Therefore, we take the locations of the infrastructure for chargers that you see on the map identified with these triangles. This comes from the work of et al. That determined optimal infrastructure locations supporting battery electric vehicle travel that is habitual on the transportation network. You can see the demand matrix for evacuees. Everyone is heading to the northeast node of 2. Arbitrarily, we decided so, and we test our model. Okay, in a case where we have dominance of gasoline vehicles on the network, we are able to construct evacuation routes that can get evacuees to safety. We track the total evacuation time, but what's most important here is that for gasoline vehicles, it's such a small network, we don't necessarily need to have gasoline vehicle drivers access refueling. So everybody can access the southern node without spending time refueling. When the network is universally utilized by vehicles with shorter driving ranges, let's say battery electric vehicles whose summation of distance can be approximated with 4 link hops in the network, then we see that we are identifying with this green highlighter all the evacuee origin nodes that would need to pass through recharging infrastructure on the way to safety. This, of course, results in rerouting from shortest paths, and you can see that's the case of nodes of evacuees that stem from nodes 19 and 20. And the total evacuation time increases by 4% during this process. This is because also the network is small and the recharging times in the process are relatively shorter. If we have only one vehicle fuel type on the network, we are also able to track the impact of the driving range on the evacuation travel time and the refueling recharging time. And of course, we can do that for any series of vehicles, but let's review the results for one vehicle type. Here you can see that in this particular Sioux Falls network, a vehicle that has a range that is shorter than 3 hops is infeasible to its center with the current charging infrastructure deployment. For 3 or more hops representing the driving range, we have feasibility and we are able to access the southern node at 2. We can track that, of course, the greater the driving range for the alternative fuel vehicle, the faster the evacuation process, and the lesser the refueling or charging time in the process. We also investigate the impact of the locations of charging infrastructure. On average, on your right-hand side, the graph signifies that for different numbers of refueling stations, you can see no refueling station on the network 1 to 5 out of the nodes that are signified as candidates by et al. Denser infrastructure placement improves evacuation and refueling and recharging time in the process. Of course, location matters. So if we take pairs of stations deployed at these potential infrastructure candidates, we can see that on average we see this improvement, but there are station pairs that would result in infeasibilities for even larger ranges, or it just the evacuation time will be longer in the process so that we can reroute everyone through this limited infrastructure on the network. We deploy our approach in the South Florida region that spans Homestead to Jupiter, including Miami, Boca Raton, and West Palm Beach. We consider that the actual center locations are the intersections with major interstates or US routes, where these enable access to the rest of the region and north. And we create a super center node. This helps us avoid to decide which destination everyone will pick, and essentially sending everyone to that super center. Okay, under universal use of gasoline vehicles, we observe that the average evacuation time is 53 minutes per vehicle. And we can still see that there is utilization of refueling infrastructure in the process. As we're introducing shares of different vehicle technologies, so gasoline and electric vehicles, 50-50 in this network, we observe an 85% increase. This is important in the travel time. This is important because this means that coordinators should consider these delays in their coordination process. And of course, we see here the properties of the evacuation plans that are guaranteed. For example, we see the property of contraflow being maintained, and as we are expecting, the property of tree being maintained for both routes. Overall, just in summary of the insights that we gained, specifications of vehicles and charging infrastructure matters. The denser the infrastructure, the faster the evacuation. However, location matters, so the deployment can result under a sparse network in infeasibilities. And it's important to also introduce the shares of vehicle fuel technologies and plan for evacuation routes that accommodate their needs. Naturally, we wanted to study potential for supplementary infrastructure deployment in these types of networks to support faster evacuations. So this is joint work with Denis Apurba and our undergraduate student Simon Balisi. You can scan and access the resource, the paper, and this is partly supported by the Illinois Indiana Sea Grant Scholarship. Okay, so we started conceptually actually exploring those topics, but then we observed that in 2024, Florida deployed mobile electric vehicle chargers to accommodate evacuation demand. So this concept was actually put into effect by agencies. As I mentioned, charging deployment on the network level is spearheaded by private investments, therefore aim to accommodate habitual needs. Maximizing profit for these entities, evacuation demand is infrequent and not considered in this process. The goal would be to couple a facility location model with the routing model that we have already developed. And we're going to introduce new constraints for accounting for the need to recharge or refuel on the way to safety that are called hop between us, and acknowledge that a vehicle might need to stop multiple times on the way to safety and not just once pass through a charger. Okay, so we have a modified network topology to account for that. So a refueling node can be either visited to actually refuel or pass through as part of your evacuation tree in the process. We use the concept of usable path. We extend this to evacuation. It's the same concept essentially. A path is usable for a vehicle fuel type with constrained range if the vehicle can evacuate to the shelter with or without refueling, but the usable evacuation path depends on the location of the charging infrastructure in our setting. The hope between us constraint, pretty much an extension of the definition of the previous tau. We introduce a new tau sub k hopes that serves as a proxy for the number of links, essentially the number of hops serve as a proxy of the total distance of the driving range of the alternative fuel vehicle. If an evacuate originates from a node such as one over here, that are tau or more hops away from a shelter, then need to pass through a station every tau hops or so. So essentially in this case, assuming that the shelter does not necessarily have recharging capabilities, this path and this path would be feasible, but not the path that would traverse through node 5. Okay, data inputs are the same as before, but now we have to account for a new added in our objective. Essentially, we need to track the investment that we allocate to support the supplementary infrastructure. There is a budget constraint so that we can have an upper bound for that. And then a similar set of constraints as we've seen before. The recourse function is there because we introduced the vendors inspired decomposition process for the location problem, and the routing problem is solved similarly with the algorithm that we've demonstrated before. In the interest of time, I'm not going to delve so much into that, but in our paper we go through the algorithmic approaches for the math heuristic solution procedure. In the outputs, we're going to have the opportunity to observe the routes that are created in the process. Of course, when we are thinking about networks designed for shorter ranges, we expect more supplementary stations to be deployed to aid to faster evacuations, and this is the case here. So 4 hops corresponds to vehicle with shorter driving ranges compared to 6 hops. The average evacuation time increases when all the vehicles have this property in the network to 255 minutes per vehicle compared to 249 minutes per vehicle for 4 and 6 hops. Accordingly, what's of interest, I think, to most is the fact that we can come up with supplementary locations for infrastructure deployment for different vehicle fuel types. So here you see a case where we have dominance of gasoline vehicles in place, 70% share, compared to 15% of shorter ranges and 15% of large range electric vehicles. The latter would constitute Tesla vehicles with supercharger nodes, and the former vehicle type 2 legacy shorter driving range vehicles, electric vehicles. In the process, we're able to determine the supplementary locations of infrastructure, and we see that we need 13 additional mobile charger locations. The average evacuation time is shorter now because we have dominance of gasoline vehicles, and these do not necessarily require frequent recharging that increases the total evacuation time. Okay. The picture changes when we are introducing greater shares of short-range vehicles in the network. So in here we have 55% short-range vehicle shares, 35% of Tesla-type electric vehicles, and 10% just gasoline vehicles. What is interesting is that we expect the average evacuation time to go up because of the recharging processes that are time-consuming. What we did not expect is to see fewer supplementary stations, but that may actually make sense because evacuation routes are now designated to avoid excessive rerouting of the alternative fuel vehicles, and particularly of the short-range electric vehicle fuel types. The process there, we can maintain the number of infrastructure that is needed. The same thing holds for the large range electric vehicles in the process. Okay, this is pretty much a summary of findings I just kind of articulated, so no need to spend too much time here. We have a few extensions in this phase, thinking about not only preemptive evacuations that suggest that the full network is operational of both opportunities to traverse links on the network without any disruption or accessing infrastructure without any power loss, but we're considering cases of evacuations that start amid the severe hazard impacts. where we would expect potentially network disconnections or power outages impacting certain charging stations. We compare and contrast preemptive and hazard impacted evacuation cases, and we track changes in travel time, refueling and recharging time, queuing, the number of evacuees that require access to infrastructure on their way to safety, share of stranded electric vehicle drivers, as well as accessibility of charging stations through a graph theoretic metric. We do the focus of our work predominantly on South Florida hurricane events, so we have categories 3 and 4 to examine. For this work, we need feedback from our FEMA resources and our colleagues that do work in hydrology in order to give us an understanding of where we should expect inundation impacts to be realized in the transportation network. And then we are able to design evacuation routes and also measure the different vulnerability metrics for both electric vehicle drivers and their infrastructure networks. Another consideration that is at play here is that we predominantly look into supply, right? Modeling the network considerations and designing evacuation routes, but we do not address the demand component. So we have an ongoing study of route choice and charging choice in networks that are under an evacuation order. We are studying the impact of vehicles' state of charge, as well as other properties in the network that have an effect on this decision making. So the news are not all that bad. We highlight that it's really important to conduct and go ahead with this decarbonization process. It's really fundamental for the agencies to take the heterogeneity of vehicle fuel types into account so that they can start their evacuation processes earlier, they can have clearer coordination for different vehicle fuel types. And for those that decide to shelter in place, there are opportunities to utilize the electric vehicle as a backup battery source. Essentially, an electric vehicle is a mobile battery device, right? So with appropriate bidirectional energy exchange, you can use this backup generator in order to power a home. And this is the use case of Ford F-150. In our simulations for the South during a summer period, we see that Ford F-150 with a 50% state of charge, 90% of the time can meet the needs of a 12-hour outage event. And again, this is even if the vehicle has a 50% state of charge. So providing important services for those that are sheltering in place during power outage events. This pretty much closes my presentation. Thank you very much for your time, and please let me know if there are any questions. Thank you.
Thank you very much, Dr. Kuntu. Questions?
Sorry, I have a question about when is the network configuration is changing, how usually we are trying to solve this problem. Because here we are essentially solving the static network planning problem, but when the network is changing, this path might not be valid.
Okay. So I think your question is pretty much tailored towards a planning versus operations type of model, right? Yes. And I think that, yes, our approach is targeting planning. So making sure that we have in advance maps, information provided to electric vehicle drivers, to gasoline vehicle drivers, denoting routes that can get them to access the pertinent infrastructure for that vehicle fuel type. When it comes to actually managing operations and the crews that are in the field, then we are talking about the need to introduce dynamics, right? So then you would have to follow a different approach in terms of routing in a dynamic traffic assignment manner, for instance, and maybe acknowledge certain coordination constraints that come from real-time or online feedback from the network. But yeah, this is one of the limitations of the study. This is kind of a planning focused result compared to an operations aimed approach that would be a bit different. Thank you for this question.
I guess I wonder, because there are some models that, for example, look at how flooding will propagate in the regions, right? And I wonder if you've considered then integrating those additional constraints, right, on the sort of, or the types of routes you can actually have in your design.
Yeah, that's a great question. Actually, we have a new research initiative that aims to do just that. So in this analysis over here, there is opportunity for example, to assess in the stochastic nature effect of the hazardous event on the network. But we don't have as granular information as what would be the impact of a certain water accumulation to the speeds that we should expect. So that's what we aim to amend right now with an extension of our study. So being able to track not only have a probability on whether certain portions of the network are operational and we can traverse or not, but also understanding how these changes would affect over time, speeds, speed limits, etc. But this is an important point. This is still ongoing. In the results that you see here, the fundamental, let's say, assumption is that we're coming up with preemptive evacuation routes. So this is way before the hurricane hits, where there is a mandatory order knowing that the hurricane is going to pass through the South Florida region, but still no impacts have been realized in the location.
For the supplementary refueling stations, is that the mobile batteries that you mentioned?
Yes.
And is it assumed that before the evacuation process you have the batteries there, or are they going to be delivered during the evacuation? Then this is going to be another set of constraints because you need some routes to those stations too.
That's an excellent question. Yes, I think the assumption is that these are already identified as the locations where they're going to be configured with portable battery storage devices that can provide recharging services. So what happened during the latest Florida evacuation preparation was pretty much the coordination agency had this information available to the motorists in advance. Just because when the actual event is on the way, it's hard to convey this information. You can imagine that they need to have a dynamic platform where they showcase where these locations of recharging stations are, and I don't think that they have something so robust set up. But that's an excellent research question. So from an emergency response standpoint, how would the fleets of coordinators be accommodated within this system? I think that's a very interesting research question. Yeah, thank you.
Do we have questions online?
If you do have a question on the Zoom, you could enter it in the chat. We don't currently have any, but we can give it a minute. Otherwise, we can feel free to wrap it up.
Okay. Thank you very much again.
Thank you so much for this opportunity. Nice to be here with you.